An interesting problem tonight about the solvability of a particular equation. And to prove whether or not this equation is solvable, we have a lemma here. And let me jump on in and prove this. Let's go ahead and set x equal to 2k plus 1. Okay. Because we're claiming that if x is odd, x squared is congruent to 1 mod 8. This is very well known from any abstract algebra book or number theory book. But notice if we square x, okay, we get 4k squared plus 4k plus 1. Like that, okay? Now notice right here, well, if you factor a 4k out here, it's kind of hard to see at first why this is important to factor it this way. You know, the expression itself does not factor very nicely, really, but whoops, this is supposed to be squared right here, okay? But notice you can factor, so we kind of partially factor it, which is sort of a trick, I guess. Take the 4k out of the first two terms, and you have this happening. 4k times the quantity k plus 1 plus 1. Okay, now notice that this part right here has to be a multiple of 8, so I'm going to write this is 8, shall we call it m? Where m's just some integer plus 1. Now you're saying, where did the 8 come from? Well, 4 is already there, right? But no, it's a parity thing. If k is odd, then k plus 1 is even, or if k is even, k plus 1 is odd. In either case, we have an even number in these successive integers, these consecutive integers. So it is equal to 8m plus 1, okay? But that's another way of saying x squared is congruent to 1 mod 8. This statement that you see right here that is vitally important to this problem, x squared is congruent to 1 mod 8, is absolutely equivalent to this statement directly above it where we showed that x was equal to 8m plus 1, okay? So we know that for any odd, you can 3 squared minus 1 is real easy to see, that's just 8. 5 squared minus 1 is 24, that's divisible by 8, and so on. 7 squared minus 1 is 48, that's divisible by 8. So you can see that it's true, we proved it, but you can see it just by discovery, you know. Now, also there's another result right here, and I said odd. Most prime numbers are odd, right? 2 is the only even prime number, so odd, and it helps out here with the prime side of this, okay? Now this very next result is true based on the fact that just x squared is congruent to 0 or 1 mod 3 period for all integers, but you have to rule out 3 here because 3 squared, of course, is just 0 mod 3, okay? So for any prime not equal to 3, we have x squared is congruent to 1. But notice that these things kind of combine in a multiplicative way, and we get this result right here, which is super important. The 24 is, of course, 3 times 8. Now, if you guys aren't familiar with modular arithmetic, what this really says is that 8 divides x squared minus 1, and 3 divides x squared minus 1, which can be written this way. But if 8 divides that and 3 divides that, then 24 divides that also, okay? So that's how that works. So we got this very important result for any odd prime not equal to 3. Now I'm not going to work the 3 part out. You can check it out case by case after the video. I'm just going to work out this more substantive part. But it's not hard to verify it manually, so to speak, for 3, okay? And even for 2, but I didn't want to mess with that because it's too much casework. All right. But anyway, so we're assuming that there's primes P, Q, M, N, and S that satisfy this equation. But if that's true, there's a corresponding congruence statement. You see, we have congruence here, not equality. Okay, mod 24. Now, that's just basic modular arithmetic. A is congruent to A, right? Because mod anything, because a minus a is 0, and any modulus divides 0. 0 is divisible by any integer, non-zero integer, okay? So this equality leads immediately to this congruence statement, all right? Now, it's very quick what's happening right here, folks. You see, if all 5 prime number variables are greater than 3, meaning 5, 7, 11, and all the other primes, you get this statement right here, because this simply would be 1 plus 1 plus 1. And right here you'd have 1 plus 1, right? So you'd have this absurd statement that 3 is congruent to 2. And that's just as absurd as saying 3 is equal to 2 with real numbers, okay? No way this is true. 24 does not divide 1 in an integer sense, right? So this implies there's no solutions. Why does it imply that? Well, we started by assuming there was a solution and got this contradiction here. Okay, we started by assuming this solution right here, and then we went through the steps here, but not much to it after that, and so there's no solution. And y'all, so it's time to write down QED. Signifying we've completed the proof here. Now again, y'all, I do want to stress there'll be people that don't listen to the video and say, well, you didn't mean, but see, I didn't prove, I just proved it for primes greater than or equal to 5. You can check it out with the inclusion of 3. And notice I did say odd prime integers here. It turns out it works for all integers, but as usual, 2 is kind of a pain in the ass on these. 2 is always a pain in the ass on a lot of number theory proofs. You have to consider it as a special case, and you have to take the time to say something about it. It does work for all primes. I just did it for all odd primes, and I didn't even finish that. I just left the work for 3. Remember, 3 squared is 9, right? It's not congruent. It's congruent to it's not congruent to 24, right? 3 squared is just equal to 9. 3 squared minus 1 is 8, which is not divisible by 24, right? So it's just too small to be. All the other primes are big enough, if you will, right? But you can check out what happens here if you try all these to be 3s and other combinations. Everything else is 1, remember? But it doesn't work out because 3 squared is such a large number in this modular sense, given the fact that everything is 1, basically, modulo 24. So anyway, that completes the proof. There are no solutions. So the answer to this question is a resounding no. Okay. That's all, and enjoy your view of the unscaled solar system.